Video, you'll learn how to make sense of organic molecules, how to make sense of the structural drawings that you see in your readings, in the learning modules, and when you search medicinal plants. Let's start with a quick review. In our last lesson, we learned that the most common elements in organic molecules each form a predictable number of bonds. There is a bonding pattern, or there are some bonding rules for the elements that we see in uncharged organic molecules. Now, the most common elements are carbon, hydrogen, oxygen, nitrogen, and sulfur. All of these elements, with the exception of hydrogen, follow the octet rule. If you recall, the octet rule is the tendency of an atom to have 8, octet, electrons in their outer shell. So the carbon atom, for example, has 4 electrons in the outer shell. It needs 4 more in order to have an octet, so it forms 4 bonds. We just said that hydrogen is an exception to the octet rule. It actually follows what we call the duet rule, and it only forms 1 bond. Oxygen and sulfur, they both form 2 bonds each, and nitrogen forms 3 bonds. Let's look at an example where we can apply these bonding rules. Here's the structural formula of an organic molecule. You can see that carbon here has 4 bonds. The carbon on the left, on the right-hand side of the molecule here, it also has 4 bonds, slightly different. It has 2 single bonds and a double bond, but the total is still 4 bonds. We can look at the oxygen, where it forms 2 bonds, and the nitrogen forms 3 bonds. This is the full structure of a molecule. What we see here is what we call the structural formula. We can see every bond and we can see every atom. But sometimes it is too tedious to write every atom, and every bond and every hydrogen atom. Let me explain. If you look at this structure, the structure on top is of a molecule called hexane. It has 6 carbon atoms. As you can see, they're numbered 1 through 6, and they're all in a chain. All the carbon atoms have 4 bonds each, and they're attached to a specific number of hydrogen atoms. You can imagine how tedious it is to keep writing these carbon atoms and hydrogen atoms. Imagine if you have a molecule with 12 or 20 or even 30 carbon atoms. So a less tedious way to represent molecules is to use the line formula, which you can see underneath here, or the bottom part of the structure. In the line formula, we can see lines, and these lines are bonds. At the end of each line, there is a carbon. When lines meet, there is a carbon. And we don't see hydrogens. We don't put hydrogens, although they are present. So let me show you here. At the end of a line, there is a carbon, and this carbon corresponds with carbon 1, in the actual full structure. And then when lines meet, there is a carbon. Lines meet here, there's a carbon. This is carbon 3, 4, 5, and 6. We can easily see the carbon skeleton in the line formula. We can also easily predict the number of hydrogen atoms that are present, even though we don't know them, based on the bonding rules that we've just seen. This makes it faster for us to draw molecules. Now, in this course, we're really not going to ask you to draw structures, but what we want to do is we want you to understand what these structures mean, and we also want you to be able to examine the carbon skeleton and simply tell the number of carbon atoms in the skeleton. Let's take a look at a question. You are given a carbon skeleton and you're asked to tell the number of carbon atoms or determine the number of carbon atoms. So I'm going to start with the chain of carbons that we see here. And I'm going to count them, So 1, 2, then 3, 4. See, when the lines meet, there is a carbon. 5, 6, 7, 8, 9, 10, and 11, 11 carbons in the main chain. And then we see some branches that also contains carbon. So 12, 13, 14, 15, 16. So this carbon skeleton has 16 carbon atoms that I've showed you here. Remember, at the end of each line, there's a carbon, and when lines meet, there is a carbon. There are more practice questions on the Blackboard course site, so do those in order to master how to tell the number of carbon atoms in a line formula.